Okay, and there. Please hear the annotation. Ah, the annotations didn't save. All right, it's fine. Let me just redraw it. Right, so we have torque is going to be our moment arm, or that'll be also radius because these are all circles. Uh, what's the cross product of that times our force, right? So it's here's a good example. Let's say this is a physics book. Let's say this is a door, right? Let's say this is a door on a hinge over here, right? So the door can swivel like this. Okay. Do we all like get the spatial analogy? Door, the hinge is on this side, right here. Okay. So if I want to apply a torque, right, I want to cause an angular acceleration for this. That would suggest I need, let's say it's at rest. I want it to start moving. Okay. If I apply a force this way, is it going to do anything? Right? If I push like into the door, is the door going to move?
Yeah.
Yeah. Oh, okay. I don't think I'm illustrating this enough. Um,
I mean, it wouldn't like move in the direction that you're pushing it, kind of.
okay. Let's say it's like a perfectly, okay. Here, let me, um,
Like it wouldn't move straight, it would move to the side.
here, let me, I'll be right back. I'm going to get a better way to show this to you. Okay, guys. Let's see if it works. So here I have like a trifold thing, right? Pretend this is like a door, okay? So, um, let's say, so here's like the hinge right over here, and I want to, if I want to cause an angular acceleration, right? I want this to go from rest, let's say it's at rest here. I want it to like, I want to close it, let's say. So I want to do this, okay? Now, it's here. If I push this way, is it going to do anything? I'm not pushing here. I'm not pushing here. I'm just
Oh.
pushing directly into it. What do we think?
It would make you tired, but nothing would happen to the door.
Exactly, right? Because I need to push it in a certain direction. I can't just push it in general for it to get to move, right? If I push it along the direction, right? Because this is the moment arm, this is the radius, right? It forms a circle around. Like this motion forms a circle, and the length of this is the radius, right? So if I push in the direction of the moment arm, sorry, ignore that, perfectly in the direction of the moment arm, it's not going to do anything, right? What I have to do is push perpendicular to the moment arm to cause it to move. Or in the other way, I have to push perpendicular. I have to push it perpendicular to the surface, right? Right, you're pushing when you're closing a door, you're pushing it perpendicularly to the length to the width of the door, right? You're not pushing into that. It's the same concept here, right? So I can't cause a torque if I'm just pushing into this. The the force, the direction of the force matters when we're talking about torque. And so specifically, it's the amount of the force vector that is perpendicular to the moment arm that's going to cause the torque. And so not just any force will produce any torque. It needs to be perpendicular to this moment arm. And then and only then can I cause an angular acceleration. So that makes a little better sense. Okay. Take that as a yes. Yeah, I think door analogy. Oh wait, that was the other one. Right. We're not done yet. No. Picture a door, right? I guess I don't really need this. But if I push the door, if I want to close it, if I push the door right at the hinge, is it going to be easier or harder to close than if I push it at the edge of the door away from the hinge? Come on. You guys feel pretty confident you guys have closed a door before.
Could you repeat the question once?
Yeah, if I push the door at the side with the hinges, will it be harder or easier than if I push it at the side without the hinges?
Pretty sure it would be harder.
Pretty sure. Have you guys never closed a door? Come on. Okay, that's your homework to practice closing a door. Try once at the edge, like with the doorknob. Okay, where do they put the doorknob? Do they put the doorknobs on the side with the hinge, or do they put them on the side without the hinge?
Oh, they put it away. They put it away from the hinge because it's harder to push the door closer to the hinge.
Exactly. And so what that you can see that with the math here, which is if it's closer to this R, right? If this R is smaller, then the torque generated is much less, right? So you're going to produce a lot more torque if you're farther from the axis of rotation, right? Because it's rotating about the hinges. If I push it further away from the hinge, it's going to be a lot easier because I'm producing a lot more torque. But if I push it really close to the hinge, I have to apply a lot of force to produce the same amount of torque. That's the other demonstration. Um, Very easy to test in your real lives. After this, go ahead and try closing a door once at the hinges, once at the edge. You'll see how much easier it is. Okay. So yeah, that was my little demo. I was just kind of to give you an intuitive explanation for this math here, because that makes a little more sense. So it's got to be perpendicular, or part of it has to be perpendicular to this moment arm, this radius. And then part of it has to be and then the amount of torque produced is proportional to how close to the axis of rotation it is. So you push it really close to the axis of rotation, this R is going to be really small. So this F has to be a lot bigger. You have to put a lot more force into it. So yeah, I hope that clarifies things. You can see it like physically. Any questions about this definition for torque? Okay then. Our next thing is moment of inertia. Moment of inertia we denote with the capital I. Oh, well, sorry, that was really bad. The capital I. Um, and this is our rotational analog for mass, right? So if torque is like a rotational version of force, moment of inertia, there's also called rotational inertia, is a rotational version of mass, basically. It's what it says, rotational inertia. Um, and so what's our definition for mass regularly?
The amount of matter in an object.
Right. And when we're talking about Newton's second law, mass is, or first law, I guess, too, mass, which is same thing as
Acceleration
inertia.
divided by force.
It's force over acceleration, but
Oh,
principally with Newton's first law, mass is a resistance to what?
change.
Change in what?
Energy, position.
Uh, I mean, I guess it's also a resistance to a change in energy, but not for a reason. It's a resistance in the change to what? You guys had it earlier. If forces cause a change in motion, what's that change in motion called?
Kinetic energy.
Acceleration.
So mass.
Acceleration.
Oh,
Kinetic energy is different. You might be getting confused with the work energy theorem, but we're talking about just force, not work here. Um, so yeah, force causes an acceleration inversely proportional to the mass. So uh, mass is going to be a resistance to acceleration, right? And so if mass is a resistance to acceleration, moment of inertia or rotational inertia is a resistance to
angular acceleration.
yeah, angular acceleration. Um, Now, moment of inertia, the math is a little more complicated because it depends on the shape. So like different shapes will have different moments of inertia. Um, I don't know if you need to really memorize the different constants from middle school. Just know the moment of inertia will usually take the form of I'm just using beta here as a constant. Mass times radius squared. Beta is just a constant. That constant changes depending on a shape, right? So for like a ring without anything in the middle, it's or it's one. For a disk, it's one half, right? So this number in front, beta, it's not a Greek letter. It just changes depending on what shape we're talking about is rotating. You don't need to know too much with it. Just again, from this, you can see that the units would be kilogram meter squared, right? Mass is kilograms, R is radius meter squared. Um, so that's moment of inertia. And so if Newton's second law relates force, mass, and acceleration, we can apply that, but for rotation, where tau equals I alpha. Right, so if F equals ma, then tau equals I alpha. Your torque is going to cause an angular acceleration, which is proportional to the or the moment of inertia, rotational inertia of the object. So this is the other equation for torque I was kind of alluding to. Here, it's just Newton's second law, right? So um, we we had these equations, like kinematics, but with rotational quantities. We have dynamics things like torque, but with rotational quantities. Um, any questions about torque? This is the like better definition. This is more just a law that relates it to two other quantities. Here, to make that clear, let me uh, there. Yeah, torque is defined as R cross F. So any questions about torque, what it is, how it works? No, Tommy, Aiden, all good. Okay, that as a yes. So we've gone over displacement, position, velocity, acceleration, torque or force and mass. what other linear dynamic quantities do we have?
Linear would be velocity,
No, just in general, what other quantities do we have?
time,
Yes.
displacement,
Yeah, so we've gone over displacement, velocity, angular acceleration, force, mass. What other quantities have we gone over? Oh, it's in the chat. Acceleration. Yeah. Like linear quantities. It's like 2 to 4 more. What did we do after going over Newton's laws?
Can I look through my notes real quick?
Yeah, you can always look through your notes, except in competition, obviously.
Oh, we did momentum and impulse.
Yeah, momentum, impulse, and what's the other one?
Net force.
That's
Oh,
force.
work.
Work, and kinetic energy, right? And so in talking about momentum, we do have an angular momentum. We use the letter L to show it, right? Um, and so if what's our formula for momentum?
Mass times velocity.
Right. So what's our rotational version of mass?
Um,
Rotational mass. Would that be the
Mo-
length of the moment arm?
no, the moment of inertia, right?
Yeah, moment of inertia. Right. This thing up here. This whatever. So mass times velocity. So if I then is our rotational analog for mass, what's our rotational analog for velocity?
Torque.
No.
Angular velocity.
Angular
Yeah,
velocity.
angular velocity. What is torque our angular version of?
Force.
Yeah. So um yeah, so if we just recreate this but rotationally you get L, which is what again?
Angular momentum.
Right? L equals I omega, which is a rotational version of mass, times our angular velocity. There you go. Works out just easy like that. Um, and an important thing is that angular momentum is always conserved. So just like momentum conservation, angular momentum is pretty big conservation thing too. Um, yeah, we can do work. So the thing about work and kinetic energy is that um, there's no rotational version of it, right? With all these other things, these are all vectors, right? And with the vectors, we have directions, but in a rotating object, that direction is always changing. Which is why they have different versions, they have different quantities between a linear version and a rotational version. But if we have a scalar, the direction doesn't really matter. It's never changing. It's just a static property of an object, which work and kinetic energy are. So we don't have a rotational version of work and kinetic energy. It's still just work and kinetic energy, but now we can introduce rotational or different forms of rotational motion into the definitions of those so that it's more comprehensive. Let me show you. So what was our formula for work?
Force times distance.
Right. force times distance. And so let's look at work, what it could be with rotational motion. So what's a rotational version of force? Come on, guys. Spend last half an hour going over it.
Could you repeat the question? I'm sorry.
What's the rotational version of force?
Torque.
Of inertia.
It's torque, yeah.
Oh my God, wait, I heard mass. I'm sorry.
Very good. And what's a rotational version of displacement or position? Which it's just the angle, theta
Oh,
here.
okay.
So yeah, if work is our force times distance, things can also do work depending on the torque they generate through an angle theta that torque goes through. Again, it's all the same. It's still work. It's not a different quantity. It's just that now rotational forces, rotational dynamics actually affects work now too. Then finally, what's our last one? Kinetic energy, right? So what's our formula for kinetic energy?
Half times mass times velocity squared.
Right. So half obviously doesn't change depending on coordinate system. What's our rotational version of mass?
Moment of inertia.
Right. And what's our rotational version of velocity?
Angular velocity.
Right.
Velocity,
So omega squared.
W.
It's omega, not W.
Uh,
It's a Greek letter. And so yeah, that's a valid equation for kinetic energy, specifically the kinetic energy stored by a rotating object. And there's a little more to it because think about a car, right? Think about a car and think about a wheel on a car. If let's say the car's moving, is the wheel rotating when it's moving?
yeah.
Right. So obviously the wheel is rotating, and if it's rotating, then it has this some kinetic energy from the rotation. But if it's rotating, is it also moving linearly?
Yes, it
Right.
is. Because it's like,
Because
yeah.
yeah, the car's moving forward, so the wheels are moving forward. And so what happened is we actually have also the meeting will end in like a couple seconds, just join back. This is an incomplete kinetic energy because let's say something's rotating and moving linearly. Then we also have that regular kinetic energy. And so this is a more complete version of kinetic energy. Now let's say it's not rotating, then this omega is zero, and so the first term goes away. And let's say it's rotating in place, so we call that rolling with slipping. Then this velocity is zero, right? And so that goes away. But more often than not, those both exist, and so you have this complete kinetic energy equation. Yeah, join back. I'm gonna end the meeting here. Just join back immediately, and we will continue.